For Hilbert's 10th problem, he wanted to know if there was a general algorithm which could tell you whether any given Diophantine equation had a solution or not. Equations are just equations, but where all of the coefficients are integers, and we're only interested in integer solutions. So the famous a to the n plus b to the n equals c to the n, the subject of Fermat's last theorem, is a Diophantine equation, because Fermat's last theorem is just saying, I want to know if this has solutions when a, b, and c are all integers, and also n is an integer. And the theorem is just saying, well, I don't think it has a solution when n is greater than 2. And this was proven to be the case. It's kind of crazy, kind of surprising, but it is the case. But for any general Diophantine equation, can we say whether it has a solution or not? Is there an algorithm which will tell us that? Well, if the Diophantine equation does indeed have a solution, then yes, there is an algorithm which will tell you that it has a solution. And it's a really simple one. It's just plugging in numbers, just plugging in the integers and seeing if they solve the equation. And if it has a solution, well, you'll get to it in a finite time. It may take a long time, but it's going to be a finite time. But what if it doesn't have a solution? Well, you can just keep on plugging in numbers forever. And indeed, it does turn out that there's no actual general algorithm that does better than that will tell you for any Diophantine equation that it doesn't have a solution. And the reason for this goes back to Turing's halting problem, which says that there are some recursively enumerable sets that are not recursive. Now, a set is recursively enumerable when you have an algorithm which can list out every element that's in that set. And because of that, there's also an algorithm which will tell you for any element that is in the set, that yes, this element is indeed in the set. But, as the halting problem showed, there are some sets like this that are not also recursive. That means that you can't also list out everything that's not in the set. And that means that you can't take any element or any number that's not in the set and have an algorithm which is going to tell you in a finite time, no, this is not in the set. And it turns out that the solutions to Diophantine equations form exactly this kind of recursively enumerable but not recursive set. And one of the people who worked on this, interestingly, was the philosopher Hilary Putnam. And in case you don't know his name, but you know the brain in the vat thought experiment, then you know his work. But a person who really put the nail in the coffin to this was Yuri Matyasevich, a Russian mathematician who proved it for his doctoral dissertation at 25.